If you know something about the derivatives and or the second derivatives, in other words, if we know about the increasing, decreasing behavior and the concavity, we can actually do a pretty good job of sketching graphs. So jumping into this, we want to think through all the possible things that we can tell. So from a function, you can tell the x and y intercepts. And this is where either x equals 0 or y equals 0. We can also, from the derivative, tell where something is increasing or decreasing, and with the first derivative test, tell where the local minima and maxima are. The second derivatives give us concavity up and down, so that's the curviness of the graph, as well as inflection points. And as a side note, with the second derivative test, we can also use this to help us find the minima and maxima. So pulling that all together, we can sketch graphs, or we can look at graphs and determine these factors. So first, sketch a graph that satisfies these conditions. There are local maxima at x equals plus and minus 1. The function is concave up for all of x, and the function remains positive for all of x. So we need to start with some sort of diagram. And if it's going to have a local maxima at x equals plus or minus 1, I'm just going to label those points in right here. So let's call this minus 1 and call this plus 1. So now if it's concave up for all of x, that means we have to have something like this in between, because it's got to be getting bigger, it's got to be smiley face, and it's got to reach a maximum at these 2 points. And then the only way for this to be a maximum is if it goes down afterwards, but if it's going to be concave up, it's got to end up doing something like this. Same thing for the other side. So it may not be this exact shape, but this is a graph that fulfills those functions. Concave up everywhere. There's all smiley faces. There's local maxima here and here, and it stays above the x-axis, so it's positive for all x. A second example, sketch a graph that satisfies all these conditions. F of x is greater than 0, so it's always positive. The derivative is greater than 0 from 1 to negative 3, or sorry, when it's greater than 1. And from negative 3 to 0, it is also, let me see, and that's also where it's greater than, the derivative is positive. And it's equal to 0 from 0 to 1. So I know this is a little bit written a little weird. I wrote it clearer in my guided notes, so you can take a look there. But we need to label our points. So negative 1, negative 2, negative 3, and 1. So it's always positive, and then the first derivative is positive for x greater than 1. So let's pick a point for x equals 1, and then it's positive. So we'll just draw some upward sloping line. And from negative 3 to 0, it's also positive. So we'll go from negative 3 to 0, just like this. And then the derivative is equal to 0 from 0 to 1. So in this section right here, we know it should be flat. So that's our key points. From negative 3 to 1, we've got some upward slope. From 1 off to infinity, we've got some upward slope. From 0 to 1, we've got a flat or no slope. We don't know what's happening to the left here, so we could put something in and say this is like asymptotically approaching the x-axis, but we know it can't go below the x-axis. So we'll leave that in kind of like so. This will make a lot more sense as you start to play with it, as you sketch things. It's another one of these skills that really comes with practice and kind of wrapping your head around it.